So the mother lode. This is a topic that has, been talked about in science since forever. It is a very a lot of people like this topic a lot. I personally like it. Um, yeah, this is going to be our first lesson on quantum theory and stuff. Now, if you try to jump into it and stuff, it's you're probably going to have to study the remedial knowledge anyway and stuff. You need a basis. This is by no means a topic that just gives itself to you for in one book and stuff. Um, so the reason why I made this actually goes into the reason why I made this and stuff. I made this because it takes so many different books and stuff to synthesize information together. So I'm synthesizing everything together so everything's coherent and logical, makes sense. Um, Helps you form better ideas in your head and more clear concepts. So here we go. The prerequisite knowledge, you must know algebra, geometry, calculus, linear algebra, and stuff. You basically knock out all of these in a 2-year mathematics program. Um, you might even squeeze in some symbolic logic there too. Stuff. Um, uh, yeah, techniques of philosophy and language skills, basic facts of science such as measurements, thinking skills, study techniques, techniques of science, natural and scientific philosophy, mathematical philosophy, mechanics, classical physics, chemistry, and stuff. Um, you learn thinking skills to be aware to kind of filter out dissonance and bias and stuff in your thinking, um, and other distorting factors. Um, Now, what do you need to have in you? What qualities does it take to be uh, a master of physics that knows this stuff? Uh, First, you need dogged determination for sure. It's not a small subject in any sense. You will have to read many books. Okay. Um, but it doesn't necessarily need to take a long time. It all comes down to, are you going to give yourself a chance to understand things? You know. Um, yeah. So yeah, you need mercy on yourself. So every time you don't misunderstand something, or whatever, you shouldn't be kicking yourself. Um, okay. You're gonna need focus, memory, especially memory permanence and stuff. You should forget as little as possible. Um, so you probably want to keep that brain exercised and stuff. You know, Mental math, including math for mechanics and other geometry-based math and stuff. If you try to tell me the mechanics doesn't have a root in geometry, I'm gonna slap the shit out of you and stuff, because that's quite possibly the dumbest thing. So we don't debate these terms, okay? Attention to detail, problem solving, visual and abstract thinking, philosophical language capacity, founded heavily in semantics and stuff. The study of physics is heavily semantic and stuff. You don't have to like go into like all the hermeneutics of like how to interpret this, interpret that and stuff. A lot of hermeneutics um, is some of hermeneutics is kind of bullshit, honestly. Um, Mental energy, because study sessions get very long sometimes. Perceptivity and emotional stability and stuff, because yeah, this stuff gets this stuff gets really heavy. Um, like studying so much can just drive a person crazy and stuff. So you have to really keep your head on your shoulders. History of quantum physics. Ancient found that the irreducibly small bits of matter with no hypothetical or theoretical way of making them smaller are called atomy and stuff. The smallest possible thing. They didn't know what it looked like and stuff, really. Um, I read somewhere the atom was formally discovered in the 1600s by some guy named Boyle or Boylan. Um, I don't really have time to go into this part too much. But yeah, they basically discovered that they discovered a few important things and stuff. If you take the Brownian motion, which generalizes the motion of an object and stuff, from such an elegant and logical construction, um, such a construction so attentive to detail and stuff that you can understand how anything moves. Okay, that's an important thing in quantum physics and stuff. So like by the late 1800s, there's a lot of scientists like going nuts and getting excited and stuff. Niels Bohr jumps in and everything. Emmy Noether comes in. Um, You could say Madame Curie and stuff um, did some work in quantum physics too, because she discovered radiation. You know, that's a quantum effect. That's quantum scale stuff. Hey, some stuff you have to understand about atoms. They only bond because each orbital has a specific. Oh, yeah, right. So the thing about atoms, um, like you, atoms have electrons that surround them, right? And so, but these electrons occur in orbitals that are respective to a certain energy level and stuff. The greater an electron has, the more it's going to want to pull away from the atom and stuff. It tends to go into the later orbitals and stuff. Atoms are mostly empty space, but the the protons and neutrons are held together by the strong force and stuff. It's very hard to break them apart and stuff. And when atoms have compatible shells, meaning that the shells can form a stable energy and stuff. Uh, there's a specific energy, and there's a way to calculate it too. Something we can discuss. Um, the the atoms, they form a molecule and stuff. We won't talk about diatoms and stuff like hydrogen and stuff. Hydrogen is often diatomic, but meaning that it's actually two atoms considered as one atom and stuff. But anyway, or something like that. It's a special case in this case, but when atoms come together to form a molecule and stuff, the orbital changes shape and it forms a unique orbital and stuff, and that just vastly changes the properties. Why? Because you have to think about this. If you're coordinating material together and stuff, it's going to have a cross product effect. The effect isn't always at a cross, right? And so because it's a cross product and stuff, you have to have it's an output of some complex function and stuff. So you want to think of something like a Cartesian product and how to generalize that and construct how to analyze it. And so then you get a very good understanding of why certain molecules have drastically different properties from the components of their parts and stuff. So there's that. So the foundational premise and stuff. We talked about Brownian motion and stuff. Now the thing about Brownian motion is that, let's see if I'm running behind. No. The thing about Brownian motion is that once you get to a very small scale, I believe it's 10 to the negative 9 nanometers or 10 to negative 20 or something. It's not a precise number, but I couldn't find the precise number and stuff. But once you get to a very small scale and stuff, gravity no longer matters and stuff. In quantum physics, gravity is really just the pull of gravitons. This is a pretty good way of explaining it and stuff, because it's doing something, so it must be made of something, right? It can't just be nothing doing something. So, and we'll talk about the mystical aspects there and stuff that could be suggested. But so when things get very small, like to the scale like an atom and some portion of that, a neutron and stuff, a boson, whatever. And we'll talk about what bosons are in a moment. Gravity no longer matters and stuff, which changes how you calculate their position and motion and stuff. And there's uncertainties about that and stuff. Once you have his acceleration, you don't necessarily have his position. Once you have his position, you don't necessarily have his acceleration. That's called Heisenberg uncertainty there. So about the thing about bosons in the Standard Model. So the Standard Model basically talks about all of the different types of particles there and stuff. Why is there so many? Well, it's because fundamentally, particles are really just wave packets and stuff. It's both a wave and a particle. They did what's called a wave-particle duality experiment and stuff, where they discovered that the mere act of observing changes whether a particle works as a particle or a wave and stuff. And when it comes to basically, and it's because quantum physics looks at the universe and stuff in a way that's completely contrary to human sense and stuff, because it has to understand everything as a sum of fundamentals and stuff. So when we look at a thing, a person, whatever and stuff, it's made out of mass and stuff, and it has energy and stuff. But in quantum physics, mass and energy are two collections of semantic detail in the same thing and stuff. When you take energy and it's condensed and forms something stable and consistent and stuff, it forms what is detectable, testable, measurable as mass and stuff. And then but mass can fully decompose into energy and stuff. Every proportion of mass has a total energy to it and stuff. And you can get a 100% conversion and stuff, and this is shown in nuclear fission. So the fundamental matter of the universe is what's called massive energy and stuff. This is fundamental component from everything from cheese to hydrogen to people, everything you can imagine and stuff. It's all fundamentally made of the same stuff and of things that vibrate at different frequencies and stuff. And fundamentally, they also vibrate at different frequencies. Bosons, mesons and stuff, they have different properties and stuff that are designated in the standard model and the extended portion of the standard model and stuff. And because of that, they're wave packets. They're particles that are also waves. They have properties of waves, just like they have the properties of particles and stuff. So quantum physics looks at everything that you can possibly think of as just changes in energy and stuff. These wave packets adopting and transmitting energy, and so even motion itself is just a change in energy and stuff. When my hand moves, this is actually just a bunch of standard model particles adopting a kinetic energy to move. So in human sense, it looks like my hand is moving, but in actuality and stuff, this is actually a type of energy transmission and stuff through this goo and stuff. What we view as vacuums or empty voids in this goo are really just they can be viewed as areas of lower density and stuff. That's still more macroscopic and stuff. In subscopic or nanoscopic, the quantum scale and stuff, everything is just different states of energy made of these wave packets. Okay. So that's like the basis of a lot of the premises for quantum physics there. Running out of breath. I should have breathed anyway. So now as far as classical mechanics go, classical mechanics can tell you how objects very large, from skyscrapers to this pen right here, behave when you throw them and stuff. It still works extremely precisely, but the techniques of quantum theory are still way more powerful. Okay, but when it comes to the motion in quantum theory and stuff, it follows quantization, which was actually discovered, I think, the late 1800s, early 1900s and stuff. One of the important discoveries they made that led to the creation of quantum physics was that there's a minimum amount of energy required to move something that has no mathematical or physical reduction to it. Like you go below that, it's not moving at all whatsoever at any level of sensitivity or detection and stuff. That's called quantized motion and stuff. So motion in quantum mechanics is all based on quantization and stuff. These little discontinuous jumps, which kind of also explains why I said that, the motion of objects in massive energy is just a shift in energy. It's basically an instantaneous shift in energy. So when you're seeking, a lot of time when you're seeking solutions on something that's like, a linear equation or a curve or a surface or whatever, you should know where that's continuous and discontinuous and why. There's that. But in classical mechanics, motion is considered continuous and stuff. You when you see those lines in the graph and stuff, it's just, there's a solution at every possible point for every area, for every point that really exists for that object. Now, what do you need to study to understand quantum physics? you need to understand algebra, geometry, calculus, linear algebra, symbolic logic. Oh yeah, so yeah, we already went to that. So um, where yeah, you need to understand the essential concepts of physics, like electricity, motion, and things like that and stuff, because these things will come up, and you will have to read them anyway to make full sense of it and stuff. And there's two ways to make sense of this stuff. You could just understand it semantically and just like read every line of everything and stuff. But you could also combine that with just understanding the concepts that you're missing and your personal understanding and stuff, so you can learn at your own pace. But you combine those together, you get the best of both worlds. Okay. Um, Now, what does it take to fully understand this? Now, Dr. Richard Feynman said that anybody thinks they understand quantum physics doesn't understand it. So, but you can, but it's 2026. It's so much easier to access the knowledge and stuff. So, you study all the topics. You don't forget them. It takes a lot of mental sweat, but you do come to understand it completely, or just understand it better than anybody else and stuff. Which means that you're basically on this treasure trove of knowledge that you could just do a whole bunch of cool stuff with. Now, what are some applications of this? Well, let's talk about. Well, quantum physics is made for quantum computers, radio technologies, nuclear fission, for nuclear energy, munitions. Sorry, quantum physics is very efficient for using energy. You know, Plausible sci-fi devices like time travel, warp drive, anti-gravity are also theoretically possible with enough understanding of this. But yeah, so what are some of the topics? Thermodynamics, Maxwell's equations, Drake equations, Boltzmann's equations, Feynman's equations, such as path integral formulation, standard model and extended, M theory, string theory, photonics, and Heisenberg uncertainty and stuff. Yeah, but quantum physics can be used for any technology or application that involves a standard extended standard model and stuff. It's awesome stuff. But yeah, this concludes part 1, and I think we covered the basis of it.